All right, it's Brian again, and today we're going to continue our week of review and synthesis. In today's class, we're going to review the concepts. Okay, we're looking at the big picture of the whole course, like what have we learned? And so it's kind of a quick review. I want to remind you, we have exam number 3 next week. The full details are on the page in Canvas. Check it out. And now let's get into this, reviewing the concepts, i.e. the big picture. This is going to be a series of exercises similar to the ones that are posted on the exam review assignment on Mastering Physics. It's a whole bunch of questions that deal with every concept of the course. We're just reviewing like all the different things we've learned, remembering the crucial pieces before we get into the like taking those concepts and applying them to the world. So these are simple questions that you should be able to answer quickly if you remember the concepts. Before we start, I want to talk about how to use the text for the course to review. And so I would say don't go through and read chapters 17 through 30 again, but do go through and look at these text boxes in the chapter. And the text boxes really kind of like capture together some of the crucial details. Like here's one box, synthesis 18.1, lenses, mirrors, and their sign conventions. This guy's got like everything we know about lenses and mirrors. You can also look at the example problems. This is kind of like how we use those concepts to solve problems. So I would say start with the highlighted bits. Now, as I said, we're going to do problems today that are intended to be done very, very quickly. When we did this in class, I played music that lasted 1 minute, and I gave people 1 minute, and then they weighed in, and we did the next problem. And so I want you to just do these quickly. So look at them, answer them. You should be able to do them quickly, and if you can't do them quickly, you should think about reviewing. So let's take a look at our first problem. A laboratory experiment produces a single slit diffraction pattern on a screen. If the slit is made narrower, what does that do to the central maximum? Think about that. I'll be back. Now in class, I would take a minute and I would say you have 1 minute to think about this. But now what I want you to do is I want you to pause the video. I want you to quickly come to an answer here. So pause the video, come to a conclusion. I'll be back. What I would do in this case is I would go to the basic relationship for the width of the central maximum for single slit diffraction. What was that relationship? Remember it, and specifically, how does it depend upon the width of the slit? So think about that. I'll be back. And if you take a look at the basic relationship, if I make the slit narrower, the central maximum will be wider. I'll let you fill in the details. Next question. You see an upright magnified image of your face when you look into a magnifying cosmetic mirror. Where is the image located? Think about it. I'll be back. Now, if it's an upright image, that tells me it's virtual. It's magnified because the mirrors that they would use for this, you would have mirrors that are converging. So rays of light come in and get bent to a focal point like so. So they're converging mirrors, and so I'm going to get a magnified image, but it will be upright, and it's upright because it is virtual. Since it's virtual, where does it appear? Yes, indeed, behind the mirror's surface. Next up. A lens creates an image as shown. In this situation, what can you say about the relationship of S and F? Think about this one for a minute. I'll be back. Well, we've got two basic relationships for lenses and images. One of them is this: 1 over F is equal to 1 over S plus 1 over S prime. And the other is H prime over H is equal to negative S prime over S. Okay? Those are our two basic relationships. I want you to think about how they relate. Now, the image is bigger than the object. The image is also inverted, and so this is a real image. Okay? This is a real image, and so that tells you some things. You can also get an additional hint, because if I look at this ray right here, this is coming in almost parallel to the optical axis. This feels focal pointy to me because that ray should go through the focal point. So with all that in hand, put those pieces together. What can you say about this? And how did I get to this answer? Think about it. Think about it, okay? Next up. Here's a question that takes us back to the start of the course. All the charges have the same magnitude, and you're thinking about the value of the electric field at the dot in each of these cases. In which case does it have the largest magnitude? Remember that. Go back and review those pieces. Give an answer. I'll be back. In the case with the largest magnitude of the field is this one right here. How did I get there? Remind yourself of the details. We're on to the next problem. A proton is released from rest at the dot. Okay? So what will it do subsequently? Read it through, think about it, remember what we learned about charges and forces and fields and potentials. I'll be back. There's a couple of different ways you can think about this. One is this. The electric field points from high potential to low potential. So the electric field points downward. That implies that the proton, which will have a positive charge is going to experience a force in the direction of the field, and so it's going to move downward. And it's moving in the direction of the field, so there's a force on it, and so it's going to move downward with an increasing speed. The other thing we could say is this. Let's think about potential and potential energy. The proton has a positive charge. Remember that the change in potential energy was just equal to Q times delta V. If I have a reduction in potential, I get a reduction in potential energy. So as the proton goes from the 0 volt line to the negative 50 volt line, it has lost potential, it's lost potential energy, and so it's gained kinetic energy. Oh, bonus question? When it gets to this point right here, what will its kinetic energy be? That's a bonus question for you to consider. That's one where you don't have to do a calculation. You can just come up with a number. But when you think this one through, what happens to the proton? It moves downward with an increasing speed, and if it goes from the point noted to the second point, as it goes from there to there, it loses a potential. It drops by 50 volts in potential. And so it loses 50 electron volts of potential energy. So how much kinetic energy does it gain? 50 electron volts. Remember that, and that's an important sort of thing to know how to do. Next up, two protons are launched from point 1 with the same speed. They follow the two trajectories shown. How are the speeds at points 2 and 3 related? This relates to the stuff we just talked about, but also the questions of like field and potential that we talked about earlier in the semester. Think about it. I'll be back. Well, remember for cases like this when we do equipotential lines for parallel plates. And if you remember, the equipotential lines were straight lines that were parallel to the plate. What that tells me is the potential at point 2 and the potential at point 3 are the same. So as a proton goes from point 1 to point 2, it changes potential energy by a certain amount, but it changes potential energy by the same amount when it goes from point 1 to point 3. So as a consequence, it's the same change in potential energy, and so therefore it's the same change in kinetic energy. I expect the speeds to be, in fact, the same. So, again, these are intended to be very, very quick. We're just illuminating these concepts. Do you remember this? And if not, go back and take a look at the crucial information. Refresh yourself of the details. We're on to the next question. An atom of helium and an atom of argon are singly ionized. They're then accelerated from rest by electric field between plates, two plates with a potential difference of 150 volts. After accelerating from one plate to another, what can we say about their kinetic energies? Think about that one. I'll be back. Okay, they're singly ionized. So what's the charge on each one? The charge on each one is just going to be equal to plus E plus the fundamental charge. So as a consequence, the change in potential energy is just going to be 150 electron volts. And so the kinetic energy that each one of them have is going to be equal to 150 electron volts. Oh, by the way, change in potential energy is actually negative 150 electron volts. They lose potential energy, so they gain kinetic energy. The kinetic energy of each one of them is going to be 150 electron volts. The fact that they have different masses will affect their speeds, but it will not affect their energies. That is determined by the potential and the charge. So think about that one. That's a bit of a head scratcher, but you should get C. Remind yourself of those details. We're on to the next question. And actually, before I do the next question, I want to talk about things I like about your generation. And since this is our last week of class, I want to do lots of things like this. Here's another thing that I like about your generation. You are a group of people that is instinctively kind. I would have to say, in the communications that people have had with me, so many of you have opened with a kind word, like, I hope that you're doing well. And thanking me for the work that I've done. You have this instinctive kindness that gives you this humanity that is truly delightful. And I know it's fashionable to say that you guys as a generation are not as awesome as those that came before. Don't let anybody tell you that. You guys rock. I love you guys to pieces. Now, here's a circuits question. What is the current through the 3 ohm resistor? We've got different options. Remember what you know about circuits. Give an answer to that question. I'll be back. Well, think about this. There's 9 volt potential difference from this battery, but positive is up here, negative is down here. 6 volts is positive up here, negative down here. If I walk around the loop and I call this one 0 volts as I do, there'll be 9 volts up here at the top left. There will be 0 volts right here because it's connected by a wire, 6 volts right here. What's the potential difference across the resistor? With the potential difference across the resistor, we can compute the current, and if you do that, you should get 1 amp. If not, go back and remind yourself of those details. Remember what we learned about circuits. We're on to the next question. A stereo amplifier creates a 5 volt potential difference across the speaker. If you want to double the power output, what do you have to change the potential difference to? Think about that one. I'll be back. Well, remember our basic expressions for power and resistance, and we had the power in a resistor was delta V squared divided by R. That was one of our possible relationships. So if I want to increase this by a factor of 2, I have to increase the voltage by the square root of 2 because it is subsequently squared. And if I take 5 volts and multiply it by the square root of 2, what I get is 7.1 volts. If you struggled with that one, go back and review the necessary concepts. We are on to the next problem. What's the value of the resistor R in this circuit? Okay, I want you to think about how you would do that. Take a minute to kind of sketch this one out. I'll be back. Now, there's 2 different ways that you could do this, and we actually solved this in class like back in the day. I could, for one, I could say, look, I got 2 amps through this combination of resistors, and the voltage across them is 8 volts. And so the effective resistance of the whole combination is just equal to the voltage divided by the current. It's equal to 4 ohms. And then I can say, oh, okay, the resistance of a parallel combination is like 1 over R1 plus 1 over R2 plus 1 over R3, and you can solve for what R3 is. You could do it that way. The other thing you could do is you could say, oh, I've got 8 volts across each one of these resistors. And so as a consequence, I can calculate the current through each one of them. I could figure out the current through the 8 for the 10 ohm resistor, the current through the 15 ohm resistor. And then the current that comes in is 2 amps. A certain amount goes here, a certain amount goes here. Anything that's left has to go here. So I'd know the current through this resistor and the voltage across that resistor. With those two numbers in hand, I could calculate the resistance. Remind yourself of how to solve problems like this. Go back and fill out the details. And when you get there, you can check yourself. And the answer should be 12 ohms. How about this one? Here's a magnet and a moving proton. What is the direction of the force on the proton? Take a minute, think about it. I'll be back. And of course, this is a right-hand rule question. And remember, we take our thumb and put it in the direction of the velocity, which is up. I take my index finger and put it in the direction of the field, which is to the left. And with the velocity is up, field to the left, the force should be out of the screen. That's a right-hand rule calculation. Remind yourself how those things are done. We are on to the next problem. A metal bar is moving through a magnetic field. And if you have a conductor moving in a magnetic, we've seen that there's a motional EMF. What will be the induced charges on the bar? Think about that one. I'll be back. Now, all the charges in the bar are moving downward. So positive charges moving downward in a field that is pointing out of the paper, because the field is pointing out of the paper. Those are B vectors. Okay, field is out of the paper. Velocity is down. Positive charges will get pushed to the left. Negative charges will get pushed to the right. And so as a consequence, I'm going to end up with the charge separation in B. And if you don't remember those details, go back, review the relevant bits. We're on to the next question. A bar magnet is pushed towards the center of a wire loop. What can you say about the induced current? Think about it. I'll be back. You're increasing the upward flux through the loop. And so the loop is going to make its own flux, which is directed downward. Okay, it's going to make a flux that goes like that. And what current would you need? And that's a case of using the one where your fingers curl around and your thumb goes in the direction of the current. I get the current is going to be going this way. And so in fact, you get, looking from above, there's a clockwise induced current in the loop. Remind yourself of those details. We're on to the next question. If the current in the straight wire is decreasing, what does that imply about the current in the loop? Think about it. I'll be back. Well, the magnetic field due to the current in the wire, and this is one of those ones where you like take your thumb in the direction of the current, wrap your fingers around the wire. You're going to get a magnetic field that goes into the screen like so on the right side. On the other side, it's coming out of the screen. But the current is decreasing, and so I've got a flux into the screen that's decreasing, and so the loop is going to make its own flux that goes into the screen. So there's an induced flux into the screen, and to produce a flux into the screen, I have to have a current that goes this way. So it's a clockwise induced current in the loop. Remind yourself of those details. You got to be able to do stuff like this with confidence. We are on to the next question. An atom has the energy levels shown. Do you expect to see a spectral line with a wavelength of 620 nanometers in this atom's emission spectrum? Think about it. I'll be back. I didn't pick 620 by accident. Remember, we said the energy of a photon was equal to 1240 divided by the wavelength. So 1240 over 620, that's just 2 electron volts. Is there a transition which would give me an energy of 2 electron volts? Well, heavens to Betsy, there is. If an electron goes from n is equal to 3 to n is equal to 2, I will have a spectral line of a 2 electron volt photon emitted. And so I will have a 620 nanometer line in the emission spectrum. Bonus question, how about the absorption spectrum? Think about that. We're on to the next question. Samples of 2 isotopes of strontium that have approximately the same number of atoms, what can you say about their activities? Think about it. I'll be back. Remember, our basic relationship for activity showed that the activity was proportional to 1 over the half-life. That makes sense. If I have a short half-life, the atoms are decaying more rapidly. A sample of atoms would thus therefore have a higher level of activity. And so you would expect that the sample with a short half-life is going to have the higher activity. Go back and review those details. Make sure you're comfortable with questions like that. We're on to the next question. Fragments of a fission reaction are isotopes that are neutron rich. So what is their most likely decay mode for these atoms? Think about it. I'll be back. If you have an atom that's just too big, it breaks into smaller pieces. And one piece it can shed as a helium nucleus. That would be alpha decay. Gamma decay doesn't change the constituents of a nucleus. They just readjust themselves, and they're just in a new arrangement. So it's not alpha decay. It's not that the nucleus is too big. It's not gamma decay. It's not that it was excited and goes into an unexcited state. It's got too many neutrons. It's got too many neutrons. And if you have too many neutrons, the way that you're going to decay is by turning a neutron into a proton plus an electron. That happens inside the nucleus. That is the hallmark of beta minus decay. Remind yourself of that crucial fact. We're on to the next question. A sealed box is completely evacuated, and then 100,000 radioactive atoms are added. After and their half-life is 2 days. After 4 days, how many atoms are in the box? Think about that one. I'm going to pause for a moment. I just want you to think about this. You have this many atoms in the box. After 4 days, the question asks, how many atoms are in the box? Well, it turns out when an atom decays, it doesn't go away. It turns into another atom. And so after 4 days, how many atoms are in the box? Just 1 million. Same number you started with. They're different species, but you have the same number of atoms. And I know that one feels like a trick question, and I would never ask a question like that on a test. Never, 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 never. But I would ask one now because it brings up an important point that when atoms decay, they don't go away. They just turn into a different atomic species. Next question. In this LED circuit, a charge is raised to a higher potential and then drops back to 0 volts as it goes through the LED. Nearly all of the lost energy is given to a single photon. Which color LED requires the highest voltage to light? So think about this. And actually, we're going to work this one through. So suppose I have photons that are given off that have an energy of 3.0 electron volts. That means the electron loses a certain amount of energy, and I get a 3 electron volt photon. How much energy was lost by the electron? 3.0 electron volts approximately. So what is the voltage of the power supply? About 3.0 volts. I wrote electron volts, sorry, about 3.0 volts. If I dial it back, and I imagine doing this not with blue light, but with red light. Red light has photon energies that are more like 2 volts. So I have 2 electron volt photons being given off. The electron loses 2.0 electron volts of energy as it goes through the LED. So as a consequence, I need a battery or a power supply with about 2 volts. So higher energy photons, it's going to require a higher voltage. Highest energy is going to be the blue ones. So if you want more experiences like that, you can take a look at the review assignment that's posted on Mastering Physics. It gives you a chance to test your knowledge of a lot of the basic concepts. And I want you to do this as a review. Go look at a problem, say, do I know how to solve this? If you don't, before you answer, go back and review. Remember the crucial pieces. This is a tool to help you review. It's not a tool to test yourself. It's a tool to help you do the review. Next time, we're going to do review, but it's going to be looking at previous exam scenarios. And then we'll also do just a little bit of closure. I'll talk to you next time.